This is lesson 2 in chapter 29, nuclear physics. And as a quick review, let's take a look at this math problem about the activity of radium. You're given the half-life in the problem, 1,600 years, which is the amount of time it would take for half of an original quantity of radium-226 to decay down into the next element that it would decay into. You're also given the quantity of your original sample, 3 times 10 to the 16th nuclei. So the first thing you're going to have to do, if you're looking at the solution part, is to be consistent with your units. You'll notice the half-life was in years, and typically we often talk about decay constants and so forth being in seconds. So the first thing we do is convert years into seconds. That's a dimensional analysis problem, and you get 5 times 10 to the 10th seconds. Then you can solve for lambda. Remember, the calculus problem is what yielded the equation that lambda, the decay constant, equals 0.693, which is the natural log of 2, divided by the half-life. And so this gives us a decay constant of 1.4 times 10 to the minus 11th per second. That's a weird looking number because of that dimension. It has the same dimensions as frequency per second. But here's how it's going to be used. In the next step of this math problem, we want to find out the activity of the sample at time 0. And in order to do that, we're going to be multiplying the decay constant by the number of nuclei. And you can see from the dimensions that when you have something per second times nuclei decaying, you get nuclei decaying per second. Once you have that piece of information, you can do a conversion factor, just like if you were converting feet into meters or joules into calories. We can convert decays per second into curies if we know the conversion factor, which is 3.7 times 10 to the 10th. So this activity originally would be 11 microcuries, because micro is a millionth, 10 to the minus 6th. Now, next, if we take the 4.8 times 10 to the 3rd, which is how much is the time frame the problem wants us to find out how many radium nuclei remain after that long period of time. If you know the half-life is 1.6 times 10 to the 3rd, you'll see that it goes into 4.8 times 10 to the 3rd 3 times. In other words, 4,800 years is the equivalent of 3 half-lives, where each half-life is 1,600 years. That means that this sample will be cut in half 3 times. And the way you can calculate cutting it in half by 3 different times, is to take your original amount, cut it in half once, cut that amount in half again, and cut that amount in half again, or you can just multiply it by 1/2 to the 3rd power, which would require you to divide it by 8. Now, when we say something decays, there is a natural decay that goes on for compounds that are naturally radioactive. And there's also the kind of decay that takes place when we have synthesized, so to speak, radioactive nuclei. That is to say, nuclei that we have made radioactive due to bombardment or a nuclear reaction. In any case, the most typical kinds of radioactive decay, and this is a test question, what are the 3 kinds of natural radioactive decay, the answer being alpha, beta, and gamma, which we're going to talk about in this page. There are other kinds of decay that are not the natural kind of decay that come from naturally occurring radioactive isotopes. But in alpha decay, the alpha is the first letter of the Greek alphabet. If you remember, Jesus is the Alpha and the Omega, the beginning and the end, referring to the beginning and end of the Greek alphabet. Well, the alpha, beta, gamma are the first three letters of the Greek alphabet, and they're named after the first three kinds of naturally occurring radioactive decay that were detected. There's some speculation that maybe there's more kinds of radioactive decay that we don't know how to detect, which would be delta and epsilon, alpha, beta, gamma, delta, epsilon. And some science fiction shows, like in Star Trek, they sometimes refer to delta radiation. But be that as it may, let's look at alpha decay. And alpha decay turns out to be nothing more than a helium nucleus. In fact, that's how we get helium in the trace amounts that we have it in our atmosphere. Radioactive decay produces alpha particles in the Earth's crust, and as a result of these alpha particles in the Earth's crust, they pick up electrons, which are everywhere available, to become helium atoms. And these helium atoms, being inert, instead of reacting with something to make a compound, they matriculate upwards and are released into the atmosphere. So we have this continuous supply of helium being produced in the atmosphere. So an alpha particle is nothing more than a helium nucleus, and this is how you would write it right here. And again, we're having trouble with the highlight aspect. Never know how that's going to look. The helium, He, the upper left is the nucleon number, 2 protons plus 2 neutrons is 4, and the superfluous or redundant bottom left, the 2, is 2 protons, which of course helium has to have 2 protons or it wouldn't be helium. Now here's some vocabulary words. We talk about the parent nucleus, which would be the nucleus on the left side of your arrow, and then whatever is produced on the right side would be the daughter products. In this case, there's primarily a daughter nucleus plus the alpha particle. And in equation 29.9, you can see that if you have your almost very, very stable uranium-238, it has a huge half-life, and it undergoes radioactive decay, as it naturally does. It'll turn into thorium. And in the process of turning into thorium, it releases an alpha particle. Now, you'll notice that the numbers in the upper left hand, 238 on the left of the arrow, equals 234 plus 4 from the alpha particle on the right side of the arrow. And the numbers in the bottom left must also add up. 92 on the left, 90 plus 2 on the right. These numbers have to be equal. Now, of course, what is not showing on the right side of the arrow is any energy or any unusual radioactive particles like neutrinos that would also be produced. More about them later, and more about calculating the amount of energy later. Another way you can do these kinds of problems is, let's pretend that you did not know what the daughter nucleus was. You knew that uranium-238 yielded an alpha particle. Well, you could take 238 minus 4 and know that your nucleon number of this daughter nucleus had to be 234. And you know that 92 minus 2 gives you a proton number of 90. And the only element that can be 90 is thorium. So you would therefore be able to identify that thorium is your daughter nucleus, just like you might have to do or will have to do on your test. Now, these are spontaneous decays. They happen on their own. You can't make them happen, you can't keep them from happening. This is a huge area of research and an area where we're kind of stymied right now, in a quandary, or we just don't know how to go about this. Some Nobel Prizes waiting to happen. If it were possible to make or prevent radioactive decay, that would be huge. Think about the radioactive waste that is left over from nuclear tests or from nuclear reactors. Wouldn't it be nice to speed up its decay or to prevent it? But that remains to be seen. So remember also that the word spontaneous does not mean immediately, all of a sudden, or without expectation. What this does mean, though, is that it will happen, but we don't know when. A given radioactive nuclei, unstable nuclei, might decay before I can finish the sentence, and it might not decay for a few more years or 1,000 years. Now, that's why we have to have this idea of a half-life. We cannot predict when an individual nuclei will decay. But we do know that if you have a statistically large enough sample of nuclei, you can predict when half of them will have decayed. Now we come down here to the bottom, and we have this equation that says kinetic energy equals momentum squared divided by 2 times the mass. This equation comes from kinetic energy equaling 1/2 mass velocity squared. And if you plug in your momentum over mass for V and square it in the equation 1/2 mv squared, you get this unusual rearrangement of terms. But the point we're trying to make with this equation is when these daughter product or products are produced, as well as the alpha particle is produced, they have momentum. They have a velocity times the mass. And as you might expect, the more massive the particle, the more slowly it's going to travel. And since an alpha particle is much less massive than a radon-222 particle, you would expect it to have a much, much higher speed. Here's another math problem. Calculate the energy released during an alpha decay. And so the equation for this alpha decay, which was on the previous page, is your radium-226 is turning into radon-222 and shooting out an alpha particle. And so the first thing we want to do is let's find out the mass of my daughter products. So we add up the mass of the radon-222 and the alpha particle, and we get the total mass of the 2 particles that have been produced. Then what we're going to do is subtract that number from the original mass of the radium. And what you find here, this is all important, is called the nuclear mass defect. This loss of mass, delta M, in nuclear physics is called the nuclear mass defect. You started with a certain amount of mass, you ended up with less. Did the mass disappear? No. It's created into energy using E equals mc squared. Or if you don't want the amount of energy produced in joules, you state it in MeVs. Because remember the conversion factor, there's 931.5 MeVs of energy per nucleon that has been converted from its mass state into its energy state. Now, beta decay is far more intriguing. In a beta decay, one thing we do know is that this electron just shoots out from the nucleus. And it's not an electron that is in one of those orbitals. When you think of atoms, you have 2 electrons in the first energy level, and you have 8 electrons in the second. This is not one of those electrons. This electron did not exist until all of a sudden it comes flying out of the nucleus and then gets captured by some atom in one of those energy levels. So where did the electron come from? Was the electron originally somewhere hiding inside the nucleus between the protons and neutrons? And of course, that's not the answer. The answer turns out to be, surprise, surprise, that a neutron in the nucleus of whatever element is showing beta decay, the neutron turns into a proton and shoots out an electron. In other words, we could oversimplify this as saying a neutron is made out of a proton and an electron. You might remember in the last lesson, we mentioned that if we were to give the mass of an electron a unit of 1, the proton's mass would be 1,836 times greater, the neutron's mass 1,837 times greater. And lo and behold, that is quite consistent here. 1,837 minus 1,836 for the proton gives me 1 for the electron. Please notice that the neutron, bottom left number, is a 0 because it does not have a charge. It has no protons. Notice that both the neutron and the proton are nucleons, so they both have a number 1 for the upper left. Now, how does a neutron do this? Why does a neutron do this? When does a neutron do this? Can you make a neutron do this? Can you keep a neutron from doing it? Excuse me. And the answer is we don't know. Not yet. It does indicate, though, that there is an awful lot that needs to be learned about the structure of a nucleus. And there is some tantalizing information coming in over the last couple of decades now that just like the electrons in an atom can be described in terms of their location quite accurately and predictively and helpfully in terms of energy levels and orbitals and spins, so we might have a very similar kind of arrangement for protons and neutrons inside the nucleus. And here's another problem where you have to find the nuclear mass defect and convert it into MeVs. Now, when this was first realized and people were beginning to understand what beta decay is, the beta particle is an electron that gets created when one of the neutrons breaks down or decays into a proton and that beta particle. It became rather obvious that something else must be going on because the electron, being so small in mass, you would think would have a huge kinetic energy in terms of its speed would be very, very, very fast. And it turns out that that is not the case. The neutron usually was not traveling all that much. And so there seemed to be some missing energy. In order to account for that missing energy, a just genius man, Italian, living in the United States, both mechanical and theoretical genius by all accounts, named Enrico Fermi, hypothesized maybe there's another kind of particle. And because he's Italian, he used kind of an Italian sounding word, a neutrino. Well, it's like a neutron, meaning no charge, and ino is an Italian for very, very little, or teeny weeny. And so he hypothesized maybe there's another particle we haven't detected yet. And lo and behold, he was entirely right. This is all done back about the years in 1940 or so. There's an interesting story about Enrico. Here you have one of the world's greatest nuclear physicists and scientific minds, and he was traveling and pulled up to a gas station to get some gas, and a guy was trying to fix his car. The attendant was, and Enrico walked up and was able to fix it, and this gas station attendant offered him a job on the spot. Now, this is not to make light of being a mechanic. The mechanics are very, very smart people in their own right and in their own field. There's lots of very, very smart people in their field that couldn't find their way around a car at all. So a neutrino is hypothesized to account for this missing mass. And as you look at the bullet points here, it has 0 electric charge. And of course, if you're neutrally charged, it makes it really hard to detect. Its mass is about as close to 0 as you might get, even smaller than an electron. And it has a spin number. The fourth quantum number for electrons is that they have positive or negative spin. Not that the number 1/2 means anything, but it's a quantized state of one or the opposite. And it doesn't interact with matter very much. You can see from these two graphs here in the right-hand margin that whereas an alpha particle in picture B would only have 4 observed energies, discrete energies, in terms of speeds, because it's a limited number of particles, the beta particle, the electron, actually has a whole range of possible speeds, including a maximum kinetic energy that you would expect if you did not have any neutrinos, but the more likely energy values, which are less than that, which means you've got to come up with something to explain the missing mass, and that's the neutrino. Now, the story gets even more interesting, because sometimes, instead of neutrinos, we get something that seems to be like just the opposite of a neutrino. And just like we now know that there are positrons that are sometimes emitted, that are just like an electron in every way, shape, and form, except they have the opposite charge, a positive charge, so there are particles that are the opposite of a neutrino. Just like a positron is an antiparticle for the electron, you have an antineutrino for your regular neutrino. And we now have been able to detect these neutrinos, though it took a while to come up with the ability to do that, because you've got to invent some pretty fancy equipment before you can carry out these experiments. Now, the third kind of naturally occurring decay is gamma decay. And a gamma decay is actually not even a particle at all, but a super high energy photon. If you can think for me, or imagine the symbol on a MasterCard credit card, those two concentric circles that overlap like a Venn diagram. Imagine that one circle represents all the different parts of the electromagnetic spectrum. You've got X-rays and UV rays and infrared rays and radio and TV and visible and so forth, and ultraviolet. And the other circle represents the different kinds of radioactive decay, like alpha, beta, and gamma. In the middle, where the two circles overlap, that's where your gamma ray is. It is both a member of the electromagnetic spectrum and a form of naturally occurring radiation, a super high energy photon that can go right through you. Now, the way that we indicate this, if we look down here at the highlighted equation 29.18, you have the carbon atom, carbon 12, but it's got a little asterisk by it. That little asterisk means it's metastable. It's not stable, but it's metastable. It's energized. It's got a little bit of extra energy. Or we could say it has ADD, so to speak. When it shoots off a gamma photon, and there's the Greek symbol for gamma, it becomes a stable carbon-12 nucleus, one that is nice and calm and no longer has the symptoms of ADD, so to speak. So that asterisk symbol means metastable, which means it's probably going to undergo a gamma decay. Notice that carbon-12 is carbon-12. Chemically speaking, it would not be different whether it's metastable or not. Now, there's lots of applications here, and one very interesting one is carbon dating. In carbon dating, we're not here talking about the kind of dates that some of you hope to be on someday. You know who I'm thinking about, or who we can always pick on. But carbon dating here means to date or to determine the date or age of a specimen. And there are lots of organic things like bones and cooking residues and vegetable matter and things like that that have carbon in them. And we can determine rather accurately how old they are using carbon dating. Sometimes it's called carbon-14 dating because it's all about the radioactive isotope of carbon, carbon-14. This is in a category of radiometric dating because this can be done with other radioactive isotopes besides carbon-12. And the idea here is that in the atmosphere, of course, we've got 79% nitrogen, nitrogen-14. And every now and then, as cosmic rays enter our atmosphere, especially from the sun, it produces different kinds of particles, including some neutrons. And if a neutron happens to smash into a carbon-12 atom, it causes it to smash into a nitrogen-14 atom, It turns that nitrogen-14 atom into a carbon-14 atom and some decay products. And that carbon-14 is radioactive. And this is happening continuously in the atmosphere. And in fact, there's a small percentage. It seems to be about maybe 1 in a trillion carbon atoms do this. But there's a small percentage of carbon dioxide that has the radioactive carbon-14 atoms that make it up. And of course, carbon dioxide is absorbed by plants in photosynthesis. And plants are eaten by animals. And so every plant and every animal and every human has trace amounts of radioactive carbon-14 in them. And radioactive carbon-14 is radioactive, so it decays. It's decaying in you right now. You are radioactive. The food that you eat is radioactive, but it's very, very low levels. And the carbon-14 is continually decaying back down into nitrogen-14. Meanwhile, you continue to eat. At least I highly recommend that. You might be eating too much. They're talking about the COVID-19 pounds that everybody's going to gain, being so sedentary. But what this means is you have a constant level of carbon-14 in you as long as you're alive, as long as a plant or an animal is alive. But as soon as the plant or animal dies, it no longer takes in carbon-14, because those of you still awake at this point recognize that when things die, they stop bringing in food. Surprise. But they still decay. So the longer something has been dead, the lower are the amounts of carbon-14 in any sample of that substance. Now we know what the background carbon-14 quantity ought to be. The carbon dioxide molecules in our atmosphere have this constant value. And we know, therefore, what that looks like in terms of radiation. I think it's about 14 decays per second. Very, very low radiation. And you take a very, very sensitive meter to detect that. And so, for example, if you had half that level of radiation, that means that this sample has been dead for half of the half-life of carbon-14. Carbon-14 has a half-life of 5,730 years. So if a sample has half of that natural radiation level, that means half of it is decayed away, so it means it's half of 5,730 years old, or about 2,400 years old. Now, we need to keep in mind that the original quantities of carbon-14 in any sample is quite small. So the number of times you can take a half-life is limited. And we estimate that you could maybe you could get 7 or 8 half-lives out of a sample. I think it's a little bit less than that to be really accurate. So we can use carbon-14 to determine the age of anything that has carbon in it, that's a big caveat, and is under, let's say, the very, very high end of 50,000 years old. Now that's interesting because many old Earth creationists think that Adam and Eve were probably created based upon the fossil record and based upon dating things like paintings and bones and other evidences of human activity. The earliest goes back about 50,000 years. I should mention that when you think of man being made in the image of God, that means man is rational, man is creative, man is spiritual, and man is relational. And so when you're looking for evidences of humans in history, you look for evidences of creativity. You look for evidences of design or tool manufacturing. You look for evidences of maybe art painting or jewelry. You look for evidences of burial of the dead and ceremony. And we typically find these things as early as 50,000 years in terms of somewhat reliable dating, and some would stretch it back even farther than that. Now, some other applications. Smoke detectors. A smoke detector typically has a little piece of americium in it. And in this chamber where the americium is, as it shoots off some alpha particles, you have these charged particles in this space where you have 2 electrodes connected to a circuit, and the charged particles complete the circuit. And as long as your circuit is completed, no problem. But if some dust from smoke gets in the way, then some of these radioactive particles activate the dust, causes a drop in the level of the current in the circuit, and that triggers an alarm and tells you you ought to get out of the house, or at least find out the source, if it's safe, for why your smoke detector went off. In the left-hand margin, you've got a little description of Enrico Fermi. He is also considered just a very, very gracious and humble gentleman. And it's nice when scientists have those godly characteristics. I do not know offhand what Enrico Fermi's worldview was. Another issue that affects a homeowner, for example, is radon. Radon, you'll recall, is an inert gas, right-hand side of the periodic table. And as elements decay and become other elements, and those elements, if they're radioactive, decay and become other elements, and you keep going down the periodic table, a lot of times at least for a while, you turn into radium before you continue to decay. Well, the radium, being inert, doesn't stay put, and it matriculates to the surface, and in some places might accumulate in a well-insulated house. And so they periodically measure levels of radon when you buy a house these days. And if it's high, you need to put a radon mitigation system in. And it would basically be a system that would keep the lower level of your house ventilated. It would exchange air, because radon, being radioactive, would contribute to the potential for lung cancer when you breathe it in. And radon would be a very, very distant second to causing lung cancers after, by far and away, the biggest cause, which would be cigarette smoke. Equation 29.19, which you probably will not have to use, is but it looks very much like the equation for half-life. Remember, half-life equals natural log of 2 divided by the decay constant? Well, here, this equation, which again comes out of the calculus, similar expressions here that we had before, basically says that if the letter R represents the present activity of a substance that is radioactive, say it has carbon-14 in it, and R sub aught, R with a little zero, is the activity series that it probably had or should have had when it was living, you take the natural log of that ratio, and you can find the half-life of this substance. Or, not the half-life, you can find T, the time, how old this substance is. Now, I should mention that the radioactive carbon content in our atmosphere does fluctuate a little bit over time, oscillating on either side of, I think, again, it's 14 decays per second. And so this has to be taken into consideration when you determine the age of something using carbon-14. But let me emphasize something about this. Carbon-14 cannot be used to date things that are older than 50,000 years. You're not going to use carbon-14 to try to determine the age of the Earth, for example, or anything, or the age of dinosaurs, or anything, dinosaur bones, or things like that. You would use other radioactive elements. But a big assumption that radioactive decay is based on is that the rate of decay doesn't change. And I think that's a very safe assumption to make, especially since we have no indication at all that the rate, the half-life of a species has changed, certainly not in recorded history, certainly not in unrecorded history in terms of going back 50,000 years and looking at records of sediments and ice cores and things like that, that there was anything that could possibly change the stability of the nucleus of an atom. The assumption becomes a little bit more substantial, of course, the older the half-life of something happens to be. And of course, this is a point of disagreement between young Earth creationists who would say the Earth is only 6,000 to 10,000 years old, and an old Earth creationist who would say that the Earth probably is 4.5 billion years old, and that dinosaurs, most dinosaurs went extinct around 60 or so million years ago, and that human beings certainly seem to be present in the geological record around 50,000 years ago. And here's a problem that takes advantage of this strategy. And I should mention, by the way, that we have proxies to compare carbon-14 dating against. We can look at known samples of things. For example, we can look at dendrochronology, tree ring samples. We can look at ice core samples. We have variations in Earth's climate because of volcanic activity that we know about. that would change the rate of growth and the size of tree rings, as well as deposits of ash in ice cores. And so, at least going back about 25,000 years, we have very good correlation between carbon-14 dating and these other ways of dating, which gives us some confidence for going back further than that, at least with carbon-14. So in this problem, you'll notice that we have our 50 decays per minute per gram as being a measurement of carbon-14 in a 50 gram sample. And we convert that into Ks per minute. Then the next thing we want to do in the second equation is, if we're going to be working in minutes, let's convert our decay constant into minutes. And then we can plug it into the equation on the previous page, and we can find out the age of this sample, which in this case would be a little over 10,000 years. So we're through talking about natural radioactivity. You can also have artificial radioactivity. And artificial radioactivity would be the result of creating nuclear reactions that don't necessarily occur naturally. And, for example, in a particle accelerator or a linear accelerator, or looking at unusual radioactive reactions, especially from cosmic rays in the upper atmosphere. And I had a fascinating week one time up at the Michigan State University in Lansing, Michigan, working with and learning about the detection of the crazy subatomic particles that you would have never heard of that seem to form in the upper atmosphere as the result of the influx of cosmic radiation. Here's an example of half-lives. It's interesting that uranium's half-life is roughly the same as that of the Earth. Other things that have a half-life less than that, we're probably not going to find any of that on the planet, because they would have long since decayed away if their half-life is substantially less. Unless, of course, there is a source that continuously produces them as the stuff that is produced decays away. And in this chart in the upper left-hand corner, it turns out we have 4 different decay series. Radioactive isotopes seem to be on one of these 4 pathways from an unstable element down to a stable isotope of lead. The previous page, let's go back, these are the 4 pathways beginning with these 4 radioactive isotopes: uranium, actinium, thorium, and neptunium, which of course is synthetic or artificial. Here is thorium-232. And if you follow along, you've got your neutron number on the y-axis, your proton number on the x-axis. If thorium does an alpha decay, it drops down 2 on the periodic table from 232, element 90 to element 88, and from a mass number of 232 drops down 4 to 228, because helium has 4 nucleons. But when you go to a beta particle, since you have a neutron turning into a proton, you go up 1 block on the periodic table. So you go from element 89 up to element 90. And then if you do an alpha and an alpha and an alpha, you lose 2 protons and 2 protons and 2 protons, till you're down to lead-212. And then you can do a beta-beta and become plutonium, polonium-212. Or you can do a beta-alpha and become thallium-208. But in either case, you're going to end up with lead-208, and then your decay series stops. Now, for the record, on your nuclear test, I'm going to give you one of these. I'm going to give you a starting radionuclide, radioactive isotope, and I'm going to tell you that this particular isotope does an alpha-alpha, beta-beta, alpha-beta, some combination, and then I'm going to say, what does it turn into? And you'll have to use a periodic table to do that, assuming I remember to give you the periodic table. And I'm going to stop right here for now, and we'll finish this chapter in the last lesson.